All right, 4.5, part 2 of 3, integration by substitution. Yesterday we talked about the steps that we use to integrate by substitution. We choose u first, and u is the thing that we know the derivative of exists there, or the thing that's on the inside of the inside function. So let's try u equals cotangent x. What's the derivative of cotangent x? The derivative of cotangent is negative cosecant squared x. Solving for dx, multiply both sides by dx. And then dividing by negative cosecant squared x. Gives us dx equals negative du over cosecant squared x. Now the next step is to substitute. We're going to replace u with cotangent of x. That's going to go, cotangent of x with u, pardon me, and dx is going to be replaced with negative du over cosecant squared x. And we'll see what happens to the rest. So we've got the square root of the substitution u. We still have our cosecant squared x. And then dx gets replaced with negative du over cosecant squared x. So the cosecant squareds cancel. The negative can come out in the front. So now we're simplifying. Put the negative out in front. Change u to the 1/2. So change the square root of u to u to the 1/2 and du. So we integrate. Add 1 to the exponent, divide by the new exponent, plus c. Remember to back substitute. So instead of u to the 3/2, we're going to have our cotangent to the 3/2 plus c. That is a 3. So that's your final answer. Probably might be written cotangent 3/2 x, possibly. They mean the same thing. So that's just a review of what we did yesterday. Now, we did talk about some certain steps. So first we'll do this example, a definite integral. You can use integration by substitution with definite integrals also. So choose u, and remember one of our hints was to choose the inside of a power as your function. Take the derivative, which would be 2x. Solve for dx, which will be du over 2x. Substitute, so we'll have the integral. Now, it's very important not to use these limits of integration when you put in the u, because this is an x value and this is an x value. These are both x values. And so if we replace our function with u, then these x values are no longer applicable, because an integral in terms of u would need u values here. All right, so there are two ways to deal with this. First, let's cancel out this x. Simplify this by pulling the 1/2 out in front. So essentially we have the integral 1/2 times the integral of u cubed du. So we should put u values here if we're going to put any numbers there at all. So we should go back up here and solve u. When you put 1 in, 2 is one of our limits, put 2 in here. 2 squared plus 1 gives us a value of 5. So when x is 2, u is 5, so we can put a 5 here. And then the upper limit is 4, so put the 4 here. 4 squared plus 1 is 17. So we can integrate now that we have u values here, because we've changed our variable of integration, we have to change our limits of integration. So let's integrate. You add 1 to the exponent and divide by the new exponent, and instead of plus c, we're going to go from 5 to 17. So that's u to the 4th over 8. from 5 to 17. So we can plug in our 17. Oops, that's an 8. And plug in our 5. And evaluate. We get 10,440.125 minus 78.125. So 10,440.125 minus 78.125 equals 10,362. Okay, that's one way to deal with the limits of integration when you use a U substitution. The other way is not writing any limits. So from this step, we write 1/2 integral u cubed du, integrate 1/2 u to the 4th over 4. Instead of plus c, we're just not going to put anything. We're just not going to have any limits of integration. But I use a bracket to remind myself that I should have numbers there eventually, so that you don't forget to put in your numbers. Then you can back substitute. So put x squared plus 1 here. And now that I have x back in there, I can use the 2 and the 4, which were the original limits of integration. So I can plug in 4, I get 17/4 over 8, and plug in the 2, and I get 17/4, 17 to the 4th, pardon me, over 8, minus 5 to the 4th over 8, which as you can see will still be 10,362. So either way makes sense to you, use it. However, you should understand both ways, because on the AP test they do talk a lot about what these limits should be if you used a certain U substitution. So they might pose a question like, if you had an integral like this and you chose this for a U substitution, what would these limits of integration change to? Something like that. So be aware how to change them. I would practice doing problems both ways so that you're familiar with them, both methods. All right, just make sure that you're not keeping the 2 and the 4 on the integrand as you work through with the letter U, because that will be counted wrong on the free response test, the free response sections. Even if you're using arrows, you can't have an integral with U in it and x values as your limits of integration. All right. The next thing I want to talk about with this is, since you have a definite integral, your calculator can find the answer for you. So remember how to find fnint. You go to Math on your graphing calculator, the Math button, and then you go down to number 9, which is fnint. And then you can either type in the function that you want to integrate, or you can have already recorded it in y1 or something and call up y1 here. Then comma x, so this is like integral function comma x from 2 to 4. 2 is the lower limit, 4 is the upper limit. Now this notation here is just the syntax for the TI-84 or 83 graphing calculator. It's not correct mathematical syntax. So if they ask you on the AP test to set up the integral or show the integral you used to evaluate, even if you can use your calculator to get the answer, they don't care about all the steps in between. If they just want you to set up the integral and then use your calculator to solve, if you write this, they will give you 0 credit for setting up the integral. They are not responsible for learning the correct syntax for every type of calculator that there is out there. And graphing calculators are used all across the world, and so is the AP test. So you're very familiar with the TI-82, 83, 84 notation, but they are not required to be. So they will not give you any credit for setting up an integral like this. If they ask you to show the integral setup, you must show this notation, the calculus proper notation, and your answer. If you just give a bald answer, as they call it, without the work or without what they ask you to show, you get 0 credit. So do not get familiar with writing this. Always write it in proper calculus notation. Always remember the dx in the end, or you'll get docked. This is not proper notation. That's just how you type it in your calculator if you're going to use your calculator. All right? They don't want to see anything like this on the AP test. All right, the new thing. That step 3 that we've been skipping over, Sometimes you need to use it, and I'll tell you when. So first you choose u. That's our inside function, right? Inside the square root seems logical. Hopefully it's obvious to you by now. Find the derivative. In this case, it's 2. Solve for dx. Remember to multiply by dx on both sides, divide by 2 on both sides, and you'll get dx equals du over 2. Substitute back into the original integral. Does anything cancel? Does everything cancel? That x right here does not cancel. If all of your x's don't cancel out, then you know you need this new step, step 3b. Unless you can choose some other u, maybe you chose u incorrectly, go back and try that. But if you're sure that's the u you're supposed to use, and your x doesn't cancel, and you have a combination of x's and u's, you cannot move forward. You need this new step, step 3. Solve for x in the u equation. So in this u equation, we're going to solve for x. So we're going to subtract 1 from both sides. We're going to divide by 2 on both sides. So we get u minus 1 over 2. Substitute that in for the x. So we're going to have the integral of u minus 1 over 2 times the square root of u times du over 2. Now all of our x's are gone. That's important. You cannot integrate until all of your variables are the same. Simplify. Pull out those 2's. They're both in the denominator, so it's going to be 1/4. U minus 1 times square root of u we can rewrite as u to the 1/2. Now this looks like it's still a product, right? But keep simplifying. Now, in this form, we can distribute. So we have 1/4, we still haven't integrated. U to the 1/2 times u to the first, we add the exponents, it's u to the 3/2. This is u to the 1/2. Now we can integrate. 1/4 times, add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent, plus c. Back substitute. 2/5 u to the 5/2, and u is 2x plus 1 minus 2/3 u to the 3/2. Now that would be fine. That leaving that answer is fine. Everything's back in where it should be. X is filled in. But on the EP test, on the in the back of our book, they will probably factor. So they're going to get a common denominator here. Multiply by 3 over 3. Multiply this one by 5 over 5. So that's going to become 6 times the quantity 2x plus 1 to the 5/2 over 15 minus 10 over 15 times 2x plus 1 to the 3/2. And then they're going to factor out what they can. So they can factor out a 15, and they can factor out from a 6 and a 10, they can factor out a 2. So what's left there is a 3, and then 2x plus 1 to the 5/2, minus, taking a 2 out of that, we've got 5, 2x plus 1 to the 3/2, plus c. So that's going to cancel to 1 over 30. Now notice these are similar, but they have different powers. They're going to factor out 2x plus 1 to the 3/2 because they both have at least 3/2 times what's left from this term is 3 times. Remember, when you factor things out, you're dividing. 5/2 and 3/2. If you divide these two, you're going to have 2x plus 1 to the 2/2 left. You subtract the exponents, so that's going to be 1. 2/2 is 1. Minus 5 times, and this whole thing we took out, so it's just 5. And then they're going to continue simplifying this. They'll multiply that in, you get 6x plus 3 minus 5. So that's going to be 6x minus 2. They might even take another 3 out of there. I think they will. So if they take another 3 out of there,